Welcome back to the channel. In the previous two episodes, we saw that because the mean and median of a distribution are the points that respectively minimize the expected values of the squared and absolute error losses, our expert in the forecasting competition introduced in an earlier episode won with the expected values submitted when the metric was mean squared error and with the medians submitted when the metric was mean absolute error. I encourage you to watch those episodes for a refresher on this. Now, imagine that the evaluation metric is MEG that we have talked about in detail in the first episode. At which point does the expert need to submit in order to bet it under MEG? To find out, we need to write down an optimization problem similar to the ones in the previous two episodes, but this time we want to find the argument of the absolute error loss. Again, watching those episodes to understand the meaning of different symbols and to get a visual intuition about what is behind the derivation that will follow is highly recommended. Simply substitute the definition of the expectation operator, break the integral into two parts, y values less than y tilde and greater than y tilde. Take y tilde out of the integrals. Set the derivative of the term inside the argument with respect to y tilde equal to 0, which results in this equation. Note that the integrand on both sides of this equation is py over y. This means that if we assume the density p is non-zero over the positive y values only, then we can view that integrand as the density of a new auxiliary random variable y sub aux, and the result of the optimization will be the median of that new random variable. So what we can say is that under absolute percentage error, the median of an auxiliary random variable whose density is proportional to the density of the original target variable y divided by that variable itself is optimal. And of course, you can have such a construct only when the density of y is over the positive values only. Going back to our competition, if our expert submits the median of that auxiliary random variable at each time step as her point forecast for that time step, then as you see here, she would win when the metric is MEG. There are some important details that I do not discuss in the videos to keep them concise. For example, how can the expert actually calculate the median of the auxiliary random variable? For such details, please refer to the GitHub repository of the channel. I now sincerely hope that the core of what we have discussed in the last 3 episodes, which is the fact that different points are optimal under different error metrics, is now clear. If it's not, or if you have any objections, please feel free to raise them as a comment or reach out. In the next episode, we will discuss some of the practical implications of what we have learned so far when it comes to evaluating point forecasts and point forecasting competitions. Thanks for watching and see you next time.